If we move into literally what's going on, all right, there's some other things that we have to understand, but let me just go to that one slide so we can sort of work this through. Okay, a few other things that we need to realize is, of course, that in any particular, most nerve cells, most are myelinated, not all, but most. And if they are myelinated, I want you guys to understand the reason why they're myelinated. Remember, as I pointed out in class, that some of you still think that this is a protein wrapped around the axon. No, it is not. These are actual cells that are wrapped around. And in the peripheral nervous system, they're called Schwann cells. And in the central nervous system, they're called the oligodendrocytes. These are actual cells. They're wrapped themselves and maintain themselves around the axon. So this is a cell-to-cell communication. All right? And then between them are these actual nodes, these gaps. Well, so what does myelination bring to the nerve cell? Well, it enables a smaller diameter axon to move an action potential upon being generated at a very amazing rate of speed. All right, and why is that? Because you can literally jump in terms of generating a current, electrochemical current. You can arc and move from here to here, from here to here, from here to here, and so on and so on and so on and so on, rather than up and down like this, all the way through here. Now we get here. Now we go up and down here. We get to here. You see, you've got to generate more. The more action potentials you have to generate per unit time or length, the slower it's going to be. That's just the reality. So myelination increases because you can literally hop that like an arc all the way down. So this thing can move down this thing much faster. As a matter of fact, in some cases, you see you have a lot of nodes here, right? In some cases, the nerve cell can even start here, generate an action potential that jumps right down to here. It actually even bypasses all of these nodes. It can be incredibly fast. It depends on which nodes are pushing the most charges at any one time. So again, the point we're trying to make here is that that's ultimately what myelination brings to it. All right. So that said, all right, what are the important players with respect to actually generating this, creating the depolarization, the repolarization, the hyperpolarization, the undershoot, the overshoot? Okay, so some of the key players. The biggest player in all of this is sodium. It's here. If you don't move sodium, nothing happens. So potassium is a player. All right, potassium is not as large a player as sodium. All right, you can move potassium all you want, but if you don't move sodium, you do not generate an action potential. So we know sodium is the big positive ion, the cation, that actually generates this, what we see right here. Okay, so that's the first thing we know. We also know that, normally speaking, all right, at a resting potential, you have a more positive number of cations on the outside than you do on the inside. So therefore you have more anions on the inside. We also know that a good portion of those anions are not chlorine. They're negative proteins found next to the surface. In other words, peripheral proteins, for example, next to the surface of the membrane. So at a resting potential, all right, that the cell is deliberately set up, this is what it's set up. Okay, and it manages that using gated ion channels. So if you want to allow sodium to move in, to facilitate the movement of sodium, then you open these channels. And then if the diffusion gradient is such, in other words, if it plays to it, and you know the charges are going to play to it, because you have more positive out here and negative in here, and you're not allowing the negative to move out. So therefore, a lot of positives are going to move in. So you will, in other words, if you move enough sodium, you will generate your first impulse. Also remember that the height, the amplitude of this one is the same as this, that you don't change this amplitude at this point. All right, so that's another important thing. And these actual action potentials are all or nothing. Okay, at this particular point. All right, where you can modulate that, remember, where you can modulate that is back here at the center. Remember. That's when you start marshalling in other molecules, okay, that can inhibit or excite. And remember, that's where a nerve cell has control over the magnitude of the action potential. So please please try to remember this. It's at the synapse that you as a nerve cell, a pre and post cell, can modulate the actual magnitude of the active potential. But once you get to here, we're done. It's gone. And that's what it's going to be until it gets to here. All right, so this is the modulatory region. A little modulation going on here at the axon hillock, and certainly at this region up here.